Hi, in this video I'd like to tell you about the total number of amoebas that ever existed in a Galton-Watson process. I would like to introduce X to be the total number of individuals that ever existed in a Galton-Watson process. Okay, so let's draw a picture. So again, here is time 0, time 1, time 2, and suppose that we have a branching here into 2. Suppose that you have another branching into 2 there, but nothing there. And suppose that the whole process stops. So then this is going to be Z0 equals 1, Z1 equals 2, Z2 equals 2, and Z3 and all other Z's really are 0. So the total number of individuals in this picture, Z3 is 0. The total number of individuals in this picture is 5. 1 plus 2 plus 2 plus 2. Okay? That's how I want to count this. Okay. Let's denote by Q the generating function of this. So expectation of S to the X. So this is the generating function for X. Okay, and I want to find out about this generating function. Now, here is what I'm going to do. I'm going to look at the first amoeba. Let me redo this picture. Maybe this amoeba here, the first one, so this is time 0. And this number here is, of course, Z1. Not this number. Z0 is 1. But this number here at time 1 is Z1. In this picture is 3. And then each of these amoeba between time 1 and time 2 decide to do their thing independently. Okay, so you might have some more branching, you might have some extinction, and so on and so on. But here is the point. The point is that if I look at this sub-branch, and this sub-branch, and that sub-branch, these are Galton-Watson processes on their own. These are, again, branching processes started each with one amoeba. And that gives rise to the following observation. If I call this X1 is the total number in this sub-branch that ever existed, is the same definition as X, the total number of individuals that ever existed in this sub-branch. And this one I could call X2, and this one I could call X3. And in general, how many of these do I have? Well, I have exactly Z1 many. In this picture, Z1 happens to be 3, but in general, I have X1, X2, X3, IID. I have X1, X2, and so on, up to X of Z1 many, IID, also independent of Z1. Also independent of Z1, random variables, and they have the same distribution as my original X I started with. Xi are equal in distribution to the original X I started with at the beginning. Okay, so that's the picture to keep in mind. And once we have that, then we can easily find an interesting identity for this generating function. So what is X in this picture? What is the total number of individuals that ever existed? Well, there are X1 many in this branch, there are X2 many in that branch, and X3 many in that branch, and there is this one that came from the beginning. So in fact, I can straight away say that x is 1 plus the sum from 1 through z1 through z1 of the xi. And that's what I'm going to plug in here. It is going to be the expectation of s to the 1, that's for the initial amoeba, plus the sum for all of the initial amoeba's offsprings of these independent and also independent of z1 xi random variables, which have the same distribution as the x. Okay? Now what am I having in here? First of all, I have a factor s, and what's left is the generating function of exactly a random sum of the type we always look at in this business. Okay, there is a factor s and expectation of s to the random sum. And I know how the generating function of s to the random sum is calculated. It's calculated like the generating function of how many I'm adding up, and inside there I have to put the generating function of what I'm adding up, and what I'm adding up has the same generating function as x. What I'm adding up has generating function q the same as x, because in distribution all these sub-branches have the same number of offsprings as x in distribution. So I have a nice equation for q of s. I know in general when somebody tells me what the branching process is, then in general I know what p is. And if I want to find qs, all I need to do is solve this equation here, and that will give me the generating function of the total number of individuals across time who ever existed, and that was qs. So let me show you an example on that in a very special case. As an example, I would like to do the following. So example is that my offspring distribution is quite simple. It is going to be 2 with probability p and 0 with probability q, which is 1 minus p. Okay, that's my offspring distribution. So it's either a branch into 2 with probability p, or it's a termination of that line of amoebas, no offsprings, with probability q. What is the mean of that? That's of course very easy to calculate. It's just 2p. In particular, the mean is equal to 1 if p is 1/2. It's of course bigger than 1 if p is bigger than 1/2, and it's of course smaller than 1 if p is smaller than 1/2, and bigger than 1 is of course supercritical. 1 is critical as usual, and this is subcritical. Okay, now let's actually find q of s for this case. So let's solve this equation. In order to do that, I need to find the generating function of this offspring distribution. That's very easy. Expectation of s to the z and j. With probability p, I have 2 for z, and with probability q, I have 0 for z. So my generating function is ps squared plus q, and that's it. And now I want to find q of s based on this equation here. So that tells me that q of s, which is the generating function for x, the total number that ever existed, okay, So Q of S is equal to S times P of Q of S. P of Q of S. What is P of Q of S? It's little p times Q square plus little q. Okay, so when I plug in Q equals SPQ, Q equals S of P of Q. That's what I have there. Okay. Now this is not very hard to actually solve for Q square. Let me drop the notation. S. So let me just write this out again without having this notation S inside, just to make life a bit simpler. So I have Q equals SPQ square plus S little q, and that means that SPQ square minus Q plus SQ equals to 0, and that I can solve. Q is 1 plus minus square root of 1 minus 4s square pq over 2sp. And now I'm in a little bit of a trouble because I need to find out whether it's the plus or the minus. These are nice functions, but I need to find out whether it's the plus or the minus. One way to find it out is to take a look at what happens when s goes to 0. I need a generating function here. When s goes to 0, I need to have some sensible quantity here. If I take the plus and take s to 0, then this term vanishes. The square root goes to 1. 1 plus 1 goes to 2. If I divide by s, which is very small, the whole thing blows up. So s goes to 0 at the plus choice will give me a problem. And that's why I can pick actually the minus. So for small s, look at small s. Use the fact that we need a generating function here because what we're hunting for is a generating function for x, so it has to be moderate for small s. And pick, based on this observation, pick the minus sign. Homework, if you pick the minus here, then for small s you have a sensible limit here. Okay, so it is going to be 1 minus the square root of 1 minus 4s squared pq over 2sp. This is the generating function for the number of all individuals that ever existed. Now I want to ask one question here, and we're going to see this kind of generating function later on a number of times, but I want to ask one question here. What is the probability that x, the total number of individuals, is finite? And if you remember, this is q at 1, because we're adding up all the mass function values. Q at 1, which is 1 minus square root of 1 minus 4pq over 2p. And 1 minus 4pq is nice. We did this before, so let me go through this fast. Q is 1 minus p, so I have 1 minus 4p plus 4p square. That's a full square. So it's 1 minus the square root of 2p minus 1 squared over 2p. Okay? Square under the square root is an absolute value. So it's 1 minus the mod of 2p minus 1 over 2p. And now I have to make a difference between p larger than 1/2 and p smaller than 1/2. P larger than 1/2 gives me 2p larger than 1. 2p minus 1 is positive. The mod of a positive number is itself. So when p is larger than 1/2, then I'm going to get 1 minus 2p plus 1, so that's 2p, that's 2 1 minus 2p plus 1, that's 2 minus 2p over 2p, which is actually 2q over 2p. So all I get here is q over p when p is larger than 1/2. When p is smaller than 1/2, then I get 2p minus 1 negative. The mod actually makes it, adds a minus sign. So mod of 2p minus 1 is 1 minus 2p. Take a minus here. In total, I'm going to have a 1 plus 2p minus 1, which is just 2p over 2p, which is just 1. Okay? So when p is larger than 1/2, then I have q over p for the probability that x is finite. When p is smaller than 1/2, then I have 1, and actually when it's equal to 1/2, then both cases work. Now, what is p larger than 1/2? P larger than 1/2 is what we had here as the supercritical case. The supercritical case has a positive probability of non-extinction. So p larger than 1/2, we have a positive probability. P larger than 1/2, we have a positive probability that x is actually infinite. It's 1 minus the line above. Oops. P larger than 1/2, the probability that x is infinite is 1 minus the line above. So it's 1 minus q over p, or it's going to be p minus q over p. And that is the probability of survival forever. This is exactly the case when the total number of individuals is infinite. This is exactly the case when the process never dies out. Okay? In the supercritical case, p is larger than 1/2, we have this probability that the process never dies out. Homework, check this, that the extinction probability is exactly q over p in that case. When p is less than 1/2, then x is finite almost surely with probability 1. We are in the subcritical region. P is smaller than 1/2. Subcritical means we do die out, so the process with probability 1 dies out, and x is going to be finite with probability 1. So that's just another check, another way of looking, at least in this example, another way of looking the extinction probability via the total number of individuals who ever existed.